power surge occurred in the eastern town of Turnhout, Belgium, resulting in damage to numerous household appliances and tools. The incident happened when an electricity company mistakenly elevated power levels to 380 volts, a substantial increase from the standard 220 volts. Following the event, the company has accepted responsibility and declared its intention to provide compensation to those affected for the damages to their equipment. Reports indicate that the power surge led to smoke emanating from various appliances, including phones, fax machines, and video recorders. A wide range of electrical equipment in numerous houses sustained damage, encompassing dishwashers, vending machines, video players, and stereos. A company spokesman has officially verified that the company will provide reimbursement for the damages incurred by the residents. A power surge is a transient overvoltage event in an electrical system. It is a sudden and unexpected increase in voltage significantly above the designated level. In standard household electrical systems, the voltage is maintained at a consistent level, for instance, 120 volts or 220 volts, depending on the region. A power surge transpires when this voltage abruptly spikes beyond the normal threshold. These surges can endure for only a few microseconds, but they can inflict considerable damage on electronic devices. Power surges can originate from various sources, both internal and external to a building's electrical system. One common source is lightning strikes. When lightning strikes near a power line, it can induce a massive voltage surge that travels through the electrical grid and into homes and businesses. Even a nearby lightning strike can generate a substantial surge. Another frequent cause of power surges is the operation of high-power electrical devices. Appliances such as air conditioners, refrigerators, and washing machines require a significant amount of electricity when they switch on or off. This switching action can create voltage fluctuations in the electrical system, leading to surges. These surges are typically smaller than those caused by lightning but can still degrade electronic components over time. Problems within the electrical grid itself can also contribute to power surges. Issues such as faulty equipment, switching operations at substations, and unexpected fluctuations in power demand can cause voltage spikes that propagate through the grid. These grid-related surges can affect a large number of customers simultaneously. Additionally, wiring problems within a building can lead to power surges. Loose connections, damaged insulation, and faulty wiring can create voltage fluctuations and increase the risk of surges. It is important to ensure that the electrical system is properly installed and maintained to minimize the risk of internally generated surges. The effects of a power surge on electronic devices can vary depending on the severity of the surge and the sensitivity of the equipment. Minor surges may cause subtle damage that accumulates over time, leading to premature failure of components. More substantial surges can result in immediate and catastrophic damage, rendering devices unusable. Sensitive electronic devices such as computers, televisions, and audio equipment are particularly vulnerable to power surges. These devices contain delicate microchips and electronic components that can be easily damaged by overvoltage. Power surges can cause a variety of problems, including data loss, hardware failure, and permanent damage to internal circuitry. Appliances with electronic controls, such as dishwashers, washing machines, and refrigerators, are also susceptible to surge damage. Surges can disrupt the operation of these appliances, causing them to malfunction or fail completely. Even seemingly simple devices like lamps and light fixtures can be damaged by power surges, leading to premature bulb failure and damage to the fixture's internal components. There are several measures that can be taken to protect electronic devices from power surges. One of the most effective is to use surge protectors. Surge protectors are designed to divert excess voltage away from sensitive equipment, preventing it from reaching and damaging the components. These devices typically contain metal oxide varistors, MOVs, which act as a shunt to redirect surge current to ground. When the voltage exceeds a certain threshold, the MOVs activate and divert the excess current, protecting the connected devices. It is important to choose surge protectors that are appropriately rated for the level of protection needed. The surge protector's dual rating indicates the amount of energy it can absorb before failing. A higher joule rating provides greater protection against larger surges. It is also important to ensure that the surge protector is properly grounded, as this is essential for it to function correctly. In addition to surge protectors, uninterruptible power supplies (UPS) can provide protection against power surges and other power quality problems. UPS contains a battery that provides backup power in the event of a power outage. It also typically includes surge protection circuitry to protect connected devices from voltage spikes. UPS is particularly useful for protecting computers and other critical equipment that need to remain operational during power outages. For comprehensive surge protection, it is recommended to install a whole-house surge protector. These devices are installed at the main electrical panel and protect all of the circuits in the house from surges entering from outside. Whole-house surge protectors are more expensive than individual surge protectors, but they provide a higher level of protection. They are particularly useful in areas that are prone to lightning strikes or have unreliable power grids. Proper grounding is also essential for surge protection. A well-grounded electrical system provides a low-resistance path for surge current to flow to ground, minimizing the voltage that reaches sensitive equipment. It is important to ensure that the grounding system is properly installed and maintained to provide effective surge protection. Regular inspection of the electrical system can help identify potential problems that could increase the risk of power surges. Loose connections, damaged wiring, and corroded grounding electrodes can all contribute to surges. Addressing these issues promptly can help prevent surges and protect electronic devices. Furthermore, it is advisable to unplug sensitive electronic devices during thunderstorms or when there is a known risk of power outages. This eliminates the possibility of surge damage from lightning strikes or grid-related voltage fluctuations. By taking these precautions, it is possible to significantly reduce the risk of damage from power surges and protect valuable electronic equipment. Now to discuss grounding and bonding more deeply. Grounding and bonding are crucial for electrical safety and surge protection. Grounding provides a path for fault current to return to the source, allowing overcurrent protective devices, such as circuit breakers and fuses, to trip and to energize the circuit. Bonding ensures that all metal parts of an electrical system are at the same electrical potential, reducing the risk of electric shock. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode, also known as a U for ground. The grounding electrode is connected to the electrical panel via a grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code (NEC). Bonding is accomplished by connecting all metal parts of the electrical system, such as metal conduits, metal enclosures, and metal water pipes, to the grounding system. This is typically done using bonding jumpers, which are conductors that connect the metal parts together. The size of the bonding jumpers is also determined by the NEC. Proper grounding and bonding are essential for the effective operation of surge protective devices (SPDS). SPDS diverts surge current to ground, protecting connected equipment from overvoltage. If the grounding system is not properly installed or maintained, the SPD may not function correctly, and equipment may still be damaged by surges. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Ground resistance testing can be used to measure the resistance of the grounding electrode system. A low ground resistance is desirable, as it indicates that the grounding system is providing an effective path for fault current to return to the source. In addition to grounding and bonding, surge protection devices (SPDS) are an important part of a comprehensive surge protection strategy. SPDS are designed to limit the voltage that reaches connected equipment during a surge event. There are several types of SPDS available, including Type 1, Type 2, and Type 3 SPDS. Type 1 SPDS are installed at the service entrance and provide protection against external surges, such as those caused by lightning strikes. Type 2 SPDS are installed at sub-panels or distribution panels and provide protection against internal surges, such as those caused by switching operations. Type 3 SPDS are installed at the point of use, such as at an outlet, and provide protection against local surges. The selection of the appropriate type of SPD depends on the specific application and the level of protection required. SPDS are rated by their surge current capacity, which is the maximum amount of surge current that they can safely divert. A higher surge current capacity provides greater protection against larger surges. SPDS also have a voltage protection rating, VPR, which indicates the maximum voltage that they will allow to pass through to connected equipment. A lower VPR provides better protection. It is important to choose SPDS that are appropriately rated for the level of protection needed. SPDS have a limited lifespan and will eventually need to be replaced. The lifespan of an SPD depends on the frequency and severity of surge events. Some SPDS have an indicator that shows when they need to be replaced. It is important to check SPDS regularly and replace them as needed to ensure continued protection. Now we'll consider power quality in its relationship to voltage and current. Power quality refers to the characteristics of the electrical power supplied to equipment. Good power quality means that the voltage and current are within acceptable limits, and that there is minimal distortion or noise on the power line. Poor power quality can lead to a variety of problems, including equipment malfunction, data loss, and premature equipment failure. Voltage sags, voltage swells, and harmonic distortion are common power quality problems. Voltage sags are short-term reductions in voltage. They can be caused by a variety of factors, such as starting large motors or switching on heavy loads. Voltage sags can cause equipment to malfunction or shut down. Voltage swells are short-term increases in voltage. They can be caused by a variety of factors, such as switching off large loads or lightning strikes. Voltage swells can damage equipment. Harmonic distortion is the presence of harmonic frequencies in the electrical waveform. Harmonics are caused by nonlinear loads, such as electronic devices and fluorescent lights. Harmonic distortion can cause a variety of problems, including overheating of equipment, increased energy consumption, and interference with communication systems. There are several measures that can be taken to improve power quality. These include installing power conditioners, using harmonic filters, and improving grounding and bonding. Power conditioners are devices that regulate voltage and filter out noise and distortion. They can be used to protect sensitive equipment from power quality problems. Harmonic filters are devices that reduce harmonic distortion. They can be installed at the service entrance or at individual loads. Improving grounding and bonding can reduce the risk of voltage sags, voltage swells, and harmonic distortion. Regular power quality monitoring can help identify potential problems and ensure that the electrical system is operating properly. Power quality analyzers can be used to measure voltage, current, harmonics, and other power quality parameters. Analyzing the data can help identify the root cause of power quality problems and determine the appropriate corrective actions. Now we'll consider electrical safety and safety codes. Electrical safety is of paramount importance to prevent electrical shocks, fires, and other hazards. Working with electricity can be dangerous, and it is essential to follow safety precautions to minimize the risk of injury or death. Safety codes such as the National Electrical Code, NEC, provide guidelines for the safe installation and maintenance of electrical systems. The NEC is a comprehensive set of standards that covers all aspects of electrical wiring and equipment. It is updated every 3 years to reflect the latest advances in technology and safety practices. The NEC is adopted by many states and local jurisdictions, and it is the basis for electrical inspections. Some key safety practices include always de-energizing circuits before working on them. Use lock-out tag-out procedures to prevent accidental re-energization. Wear appropriate personal protective equipment, PPE, such as insulated gloves and safety glasses. Use insulated tools when working on electrical circuits. Never work on electrical equipment in wet conditions. Inspect electrical equipment regularly for damage. Replace damaged equipment immediately. Do not overload circuits. Use extension cords safely. Do not run extension cords under rugs or furniture. Do not use extension cords as a permanent wiring solution. Install ground fault circuit interrupters (GFCIs) in wet locations such as bathrooms and kitchens. GFCIs protect against electric shock by detecting ground faults and interrupting the circuit. Install arc fault circuit interrupters (AFCIs) in bedrooms and other living areas. AFCIs protect against electrical fires by detecting arc faults and interrupting the circuit. Follow the manufacturer's instructions for the installation and use of electrical equipment. Obtain a permit and have the work inspected by a qualified electrical inspector. Electrical inspections ensure that the work is performed in accordance with the NEC and other applicable codes. Regular training on electrical safety practices is essential for all workers who work with electricity. Training should cover topics such as hazard recognition, lockout-tagout procedures, and the proper use of PPE. Emergency procedures should be in place in case of an electrical accident. Know the location of the main electrical disconnect and how to shut off power in an emergency. Have a plan for providing first aid to victims of electrical shock. Electrical safety is a shared responsibility. By following safety precautions and adhering to safety codes, we can all help prevent electrical accidents and create a safer working environment. And finally, power distribution systems. Power distribution systems are the networks of electrical equipment that deliver power from the generating source to the end users. These systems include transmission lines, substations, distribution lines, transformers, and other equipment. Transmission lines carry high voltage power over long distances from generating plants to substations. Substations reduce the voltage of the power to levels that can be used by distribution systems. Distribution lines carry power from substations to individual customers. Transformers further reduce the voltage of the power to the levels used by homes and businesses, typically 120 volts or 240 volts. Power distribution systems can be classified as radial, loop, or network systems. Radial systems have a single path for power to flow from the source to the load. Loop systems have multiple paths for power to flow, providing redundancy and improved reliability. Network systems have a complex interconnected grid that provides multiple paths for power to flow, offering the highest level of reliability. The design of a power distribution system depends on a variety of factors, including the load density, the reliability requirements, and the cost. High load density areas, such as urban centers, require more robust distribution systems than low load density areas, such as rural areas. Critical facilities, such as hospitals and data centers, require highly reliable distribution systems. The cost of the distribution system must be balanced against the reliability requirements. Power distribution systems are becoming increasingly complex with the integration of renewable energy sources such as solar and wind power. These distributed generation resources can inject power into the distribution grid, requiring new control and protection strategies. Smart grids are power distribution systems that use advanced communication and control technologies to improve efficiency, reliability, and security. Smart grids can monitor and control the flow of power in real time, allowing for better management of distributed generation resources and improved response to outages. Maintenance of power distribution systems is essential to ensure their reliability and safety. Regular inspections and testing can identify potential problems before they lead to outages or equipment failures. Maintenance activities include inspecting transmission lines for damage, testing substation equipment, and replacing aging components. Safety is a paramount concern in the operation and maintenance of power distribution systems. Workers must be properly trained and equipped to work safely around high-voltage equipment. Safety procedures must be followed to prevent electrical shocks, arc flashes, and other hazards. Understanding electrical concepts such as voltage, current, resistance, power, grounding, and bonding is essential for anyone working with electrical systems. It is also important to be familiar with electrical safety codes and standards. A strong understanding of these concepts and practices can help prevent electrical accidents and ensure the safe and reliable operation of electrical systems. The incident in Belgium serves as a stark reminder of the importance of maintaining proper voltage levels and implementing robust surge protection measures to safeguard electrical equipment and ensure the safety of residents.